registration number is 23TE22. Today I'm going to talk about how artificial intelligence makes decisions. We will look at how logical agents and the different ways they connect the dots using things like forward chaining, backward chaining, and first order logic. So let's get started. Logical agents. Think of a logical agent as a smart computer program. Unlike simple programs that just follow rigid steps, a logical agent has a brain called a knowledge base. It stores facts and rules. When it faces a new situation, it uses logic to figure out the best action to take rather than just guessing. Over here, we can see that the interaction with the knowledge base is driven by two fundamental logical operations. The tell operation inserts new facts or perceptions into the knowledge base, and the ask operation it queries about the knowledge base to deduce rational actions. Now, what is inference engine? It deduces answers mathematically. There are three levels to represent logical agent architecture. The first level is knowledge level. The higher abstract tier, you describe what the agent knows. For example, the gold is in the room number 1 or 2. Then we have the second level of representation, that is implementation level. There it's just how the knowledge is structured into programmatic statements or logical formulas inside the system database. The third is the goal of inference. It means deducing hidden features of the environment from history and executing sequence actions that safely maximize utility. We can also understand logical agents with the help of an example. If I were to say, a great example is the smart vacuum cleaner. It doesn't just drive around randomly, it looks at its rules. If it senses there is dirt here, it uses its logic to decide, I must turn on the vacuum. It senses the world, checks its facts, and takes action. Now, how do these agents solve problems? One way is through propositional logic resolution. This is a fancy term for a simple idea, process of elimination. If you know that at least one of the two things must be true, and you find out the first one is false, then the second one absolutely must be true. We can understand this with the help of an example. Let's say our rule is, it is either raining or it is sunny. Then you look out the window and see a new fact. It is not raining. By combining these two pieces of information, the system resolves the conflict and correctly concludes, therefore it must be sunny. Next is forward chaining. Think of it like a detective putting together clues at a crime scene. It is a bottom-up approach. You start with the basic facts you know right now, apply your rules, and keep discovering new information until you reach a final conclusion. It has many core applications, but we'll be talking about real-time automated scheduling and logistics, industrial system control and manufacturing pipelines, automated telemetry alert triggers. For example, let's say our starting facts are, it is raining and you don't have an umbrella. Our first rule says, if it rains and you have no umbrella, you get wet. So, the system adds, you get wet to its facts. Our second rule says, if you get wet, you catch a cold. The system moves forward from the facts and reaches the final conclusion. You will catch a cold. This is how forward chaining executes. Backward chaining. Backward chaining is the exact opposite. Think of this like a doctor trying to diagnose a patient. It is a top-down approach. You start with your final goal or a hypothesis, and you work backward to see if you have the evidence to prove it. Its core applications include clinical medical diagnostic systems, system telemetry debugging and troubleshooting, logic-based compiler optimizations. Using the same scenario, imagine your goal is to answer the question, will I catch a cold? The system works backwards. It says, to catch a cold, do I need to get wet? Yes. Then it asks, to get wet, is it raining? And am I missing an umbrella? It checks the database for those specific facts If those facts exist, the system says, yes, the hypothesis is proven. In this way, you can execute backward chaining. AI deals with the real world. Basic logic isn't enough. We need first order logic or FOL. Basic logic just deals with simple true or false statements. FOL lets us talk about specific objects, their properties, and how they relate to each other. It also tells us use words like all and some, which we call quantifiers. Okay. Look at how we translate everyday English into first order logic. First, we have every engineering student likes coding. Because this applies to everyone, we use the universal quantifier, which is the upside down A, for all. It tells the computer if a person is an engineering student, then they like coding. Second, we have some networks are secure. Over here, we can say that the word some represents existential quantifier, that is the backward E. It tells the computer that some networks exist that are secure. In this way, we can execute first order logic, or we can translate first order logic into our everyday basic English. How does the system actually learn new things using FOL? We call this FOL inference. The most common trick it uses is taking a general universal rule that applies to everyone and applying it to a specific person or object to create a brand new fact. Here's how it works in action. Rule 1 says all engineers are analytical. Fact 2 says Andrew is an engineer. The system strips away the word all and plugs Andrew's name directly into the rule. Because Andrew is an engineer, the system creates a brand new conclusion: Andrew is analytical. In this how we use FOL inference. We can say that logical agents use facts to make smart decisions. Forward chaining helps them guess what happens next based on clues, while backward chaining